Hello and welcome to all of you. Today I'll be talking about neutrinos, and I would like to talk about their origin, and I would basically like to introduce you with the particles that are passing through our body. Uh, uh, Millions of these particles are passing through our body, and they are passing through the matter uh, that is surrounding us. So the target of this video is to basically to have a know-how about the proposed particles known as neutrinos. So I would like to endorse some of the important implications of these particles and the physics that is surrounded uh, uh, across these particles, what we call as neutrinos. So the target will be like to have definition, the origin, conformation, and the possible applications of these particles known as neutrinos. So to introduce you with the neutrinos, they are they are they are they are fundamental particles. They don't have any charge the way we have particles like electrons and protons. The charge of electron is negative and the charge of proton is positive. These neutrinos, they don't have any charge, and they may have a mass, and that mass is very small. And I'll tell you that what are the possible implications, the experimental outcomes that dictate us that these neutrinos have masses, and the magnitude of that mass is very small. So what they do is they interact. We find their interaction via weak nuclear force, and they do interact gravity, and this is what makes them extremely difficult to be detected, because they don't interact with something strong. They interact with weak nuclear forces, and they possibly interact with gravity, and gravity is the weakest of all. So talking about its historical background, what we have is the existence of these particles was proposed by Wolfgang Pauli in 1930, and what was the target was to explain the missing energy in the beta decay. As we know that we have some of the nuclei which are radioactive in nature, and what they do is they emit particles, alpha particles, beta particles, and gamma particles. So the missing energy that could not be explained during the beta decay, a particle was proposed by the Pauli, the Wolfgang Pauli, and he later named the name that was given to this particle was Enrico Fermi, and he named this particle as the neutrino. So we have the types of the neutrinos. What we have three types of neutrinos, and the types, when we say that there are types, you got to have differentiation of type 1, type 2, and type 3. And what we call that differentiation is enunciated using the flavors. We call it flavors of neutrinos. So what we have electron neutrino, that's new. E, then we have muon neutrino, this is another type, and then we have the tau neutrino. These are the three important categories of neutrinos. Now, talking about the properties of neutrinos, as I said, they have very small mass, they don't have any charge, and what they do is they travel with the speed that's close to the speed of the light. So, what they do in addition to that, they oscillate. So since you have the category of these neutrinos, there is an oscillating nature that's experimentally observed, that their flavors change, they keep on changing. The puzzle that we have, if we talk about the puzzle, the neutrino puzzle, the solar neutrino problem, talking about the neutrinos that are developed and in solar, the discovery that neutrinos change flavors, what they do basically is it's indicating that they must have some mass. As I said, that you have the category and there is oscillating nature of these particles. Their flavor changes from one state to another state. This oscillating nature certainly indicates that these particles must have some mass, and having mass, assigning mass to the neutrinos is something that's contrary to the early assumptions of this particle. Okay, so origins can be many. There can be many origins where from the neutrinos are produced, and they are produced in nuclear reactions, as those we find in sun. You have nuclear fusion in the sun, and neutrinos are formed in that. The neutrinos are formed in nuclear reactors where you have nuclear fission taking place. The supernova, the old star, when it exhausts all of its hydrogen, there is a gravitational collapse of a star. This collapse gives birth to an explosion, a huge explosion, what's called as supernova. The supernova, this explosion from the stars, is also the source of neutrinos. And obviously we know that a lot of cosmic rays are coming from the outer universe. They do interact with the atmosphere of the planet. So while interacting, they produce different particles, and there is production of neutrinos as well due to these cosmic rays. So talking about the neutrinos from the sun, as I said, they are generated through the nuclear fusion. So as we understand, there is nuclear fusion going on inside a living sun, where the two hydrogen atoms coalesce and they give rise to the helium. But at the same time, there is a tremendous amount of energy produced by combining the two hydrogen atoms. So what we have these are the natural fusion reactors, fusion reactions. So the sun's core is something that provides the insight into the solar process. So what we have neutrinos that are produced from the core of the sun. So if we manage to detect these particles that are originated from the core of the sun, they certainly will come up with some information regarding the core of the sun. Then we have atmospheric neutrinos, as I was talking about, the cosmic rays coming on and interacting with the atmosphere, leading to the production of neutrinos. So they are produced when cosmic rays strike the atoms in the Earth's atmosphere. So creating the showers of the particles, including neutrinos. It's not only the neutrinos that are produced, there are different kinds of particles that are produced in the atmosphere, but in addition to these particles, there is production of these neutrinos. In reactor neutrinos, we have these neutrinos are emitted during the beta decay of the nuclear fission products in the nuclear reactors. So you have nuclear fission, and this nuclear fission leads to the production of the neutrinos, where we can set up that conservation, the conservation of of charge, the conservation of mass, the conservation of energy, that led us to predict the existence of these particles. So useful in neutrino oscillation experiments. So the nuclear reactor problems that are going on around the globe, they can also be assumed to be the seeds of producing these neutrinos. Supernova, as I said, you have a vast number of neutrinos. They are released during the supernova explosion, as I talked about that. And what does they do? They offering clues about this stellar collapse, because supernova is a result of the gravitational collapse of the star. And at that time, you have the bunch of showers of neutrinos that are produced during the supernova. So certainly offering us the clues about the collapse of the star. Neutrino oscillations, which I believe is a basic experimental result that we have obtained that tells us that neutrinos must have mass. So what we have here, it's a phenomenon where a neutrino changes its flavor as it travels. So changing flavor, it's a very good signature of assigning the mass to these particles. And this oscillatory nature of neutrinos, changing the flavors, proves that neutrinos must have mass. Then we have experimental confirmation of neutrinos, and they are confirmed by home-state experiment and later by super Camaricon and SNO, which showed the oscillatory nature of the neutrinos changing the flavors, and that led us to conclude that neutrinos must have mass. The major experiments, if we talk about the key experiments, what they include is a super Camaricon, SNO, and CAM land, and ice cube. These are the robust experiments that have been conducted around the globe, leading us to conclude that neutrinos must have mass. So we have detection techniques. We can detect these neutrinos, and they are detected by interactions. As I said, they weakly interact with the weak forces, and they don't interact with the gravity. So what different techniques are originated? The different techniques are built basically to detect these neutrinos, and the examples like Lorenz detectors, which are filled with water, ice, or maybe some special materials of special interest that can show an interaction with these particles, which are continuously passing through us. So neutrino mass, as I said, you have this is the only evidence that tells us that these neutrinos have the mass, but still it's an open question in physics. So the measurements from these oscillatory experiments, the oscillation experiments that have been conducted around the globe, they only provide basically, you're not actually measuring the mass of these particles, they provide you the difference in the masses, because you have the transition of the flavors. You have neutrino of state 1 going on into the neutrino of state 2. You can calculate the difference of the masses while making that transition, but they don't give us the exact measurement of the mass of the neutrino. So neutrinos are very key in the framework of standard model. So what neutrinos does, they challenge the standard model as it originally assumed massless neutrinos. So the current experimental evidences that are available to us, they are dictating us something that goes against the standard model, because standard model assumes that neutrinos do not have, they don't carry any mass. These are the massless particles. Okay, what we have sterile neutrinos. These are hypothetical neutrinos that do not interact. They're sterile. They don't interact. They don't interact via weak force, but they interact only through the gravity. And they could be the key particles to explain the dark matter. Neutrinos, the whole cosmos is filled with neutrinos, and certainly it influences the evolution of the universe. So to have better and better understanding about these particles, we can have better understanding of how the universe has evolved from the current theories. We can understand that how the universe has come to the present times. So it plays a role in the formation of large scale structures. So they have a key role, even though they are minor particles, and they certainly play a very important role in the formation of the large structure that we could see around us in the cosmological world, where we have billions of galaxies surrounding us. So they are certainly the builders of those large-scale structures. Certainly, this physics has applications, it has implications, and it certainly has something extraordinary in it, because if you understand it correctly, you can understand the cosmos correctly. So what does the applications include? Nuclear reactor monitoring, geophysical studies, and astrophysical observations. These are the current implications where you can apply the neutrino physics and the particles that we have been talking about. So the future prospects are, we have experiments, they aim to determine the absolute mass of the neutrinos, because as I said, that there is a signature of having mass to these neutrinos, but the mass of the neutrino is not directly calculated. What we can infer is the difference in the mass while studying the oscillatory nature of the flavor of these particles. So what we have to approach in future to calculate the absolute mass of neutrinos and whether they are the so-called Majorana particles. So to conclude this brief introduction to the particles, neutrinos, and certainly the framework is the framework of the physics. What we conclude is that neutrinos, they certainly remain one of the most mysterious particles in the cosmos, and people are working. Their work is continued to unravel the secrets of the universe in the view of understanding what neutrinos are and how they play their crucial role in building this huge cosmos. So with this, I'd like to stop, and goodbye.